Piping. Within industry, piping is a system of pipes used to convey fluids, liquids, and gases from one location to another. The engineering discipline of piping design studies the efficient transport of fluid. Industrial process piping and accompanying in-line components can be manufactured from wood, fiberglass, glass, steel, aluminum, plastic, copper, and concrete. The in-line components, known as fittings, valves, and other devices, typically sense and control the pressure, flow rate, and temperature of the transmitted fluid, and usually are included in the field of piping design or piping engineering, though the sensors and automatic controlling devices may alternatively be treated as part of instrumentation and control design. Piping systems are documented in piping and instrumentation diagrams P&ID. If necessary, pipes can be cleaned by the tube cleaning process. Piping sometimes refers to piping design, the detailed specification of the physical piping layout within a process plant or commercial building. In earlier days, this was sometimes called drafting, technical drawing, engineering drawing, and design, but is today commonly performed by designers that have learned to use automated computer-aided drawing or computer-aided design CAD software. Plumbing is a piping system with which most people are familiar, as it constitutes the form of fluid transportation that is used to provide potable water and fuels to their homes and businesses. Plumbing pipes also remove waste in the form of sewage and allow venting of sewage gases to the outdoors. Fire sprinkler systems also use piping and may transport non-potable or potable water or other fire suppression fluids. Piping also has many other industrial applications, which are crucial for moving raw and semi-processed fluids for refining into more useful products. Some of the more exotic materials used in pipe construction are Inconel, titanium, chrome moly, and various other steel alloys. Engineering subfields. Generally, industrial piping engineering has four major subfields: piping material, stress analysis. Process piping and power piping are typically checked by pipe stress engineers to verify that the routing, nozzle loads, hangers, and supports are properly placed and selected such that allowable pipe stress is not exceeded under different loads such as sustained loads, operating loads, pressure testing loads, etc., as stipulated by the ISME B30. It is necessary to evaluate the mechanical behavior of the piping under regular loads, internal pressure, and thermal stresses, as well under occasional and intermittent loading cases such as earthquake, high wind, or special vibration, and water hammer. This evaluation is usually performed with the assistance of a specialized finite element pipe stress analysis computer programs such as AutoPipe, KeyPipe, Caesar, Pass/Start Prof. In cryogenic pipe supports, most steel become more brittle as the temperature decreases from normal operating conditions, so it is necessary to know steel structures will have areas of high stress that may be caused by sharp corners in the design or inclusions in the material. Materials. The material with which a pipe is manufactured often forms as the basis for choosing any pipe. Materials that are used for manufacturing pipes include carbon steel, Aston AT 152 spec grade 1, grade 2, grade 3 steel pile pipe, plastic piping, e.g. HDP pipe, PPR pipe, or LDP pipe, low temperature service carbon steel, stainless steel, non-ferrous metals, e.g. copper-nickel, tantalum-lined, etc., non-metallic, e.g. tempered glass, Teflon-lined, PVC, etc. History. Early wooden pipes were constructed out of logs that had a large hole bored lengthwise through the center. Later wooden pipes were constructed with staves and hoops similar to wooden barrel construction. Stave pipes have the advantage that they are easily transported as a compact pile of parts on a wagon and then assembled as a hollow structure at the job site. Wooden pipes were especially popular in mountain regions where transport of heavy iron or concrete pipes would have been difficult. Wooden pipes were easier to maintain than metal, because the wood did not expand or contract with temperature changes as much as metal, and so consequently expansion joints and bends were not required. The thickness of wood afforded some insulating properties to the pipes, which helped prevent freezing as compared to metal pipes. Wood used for water pipes also does not rot very easily. Electrolysis does not affect wood pipes at all, since wood is a much better electrical insulator. In the western United States, where redwood was used for pipe construction, it was found that redwood had peculiar properties that protected it from weathering acids, insects, and fungus growths. Redwood pipes stayed smooth and clean indefinitely, while iron pipe, by comparison, would rapidly begin to scale and corrode, and could eventually plug itself up with the corrosion. Standards. There are certain standard codes that need to be followed while designing or manufacturing any piping system. Organizations that promulgate piping standards include ASME, the American Society of Mechanical Engineers B31 series, ASME B31.1 power piping, steam piping, etc. ASME B31.3 process piping, ASME B31.4 pipeline transportation systems for liquid hydrocarbons and other liquids and oil and gas, ASME B31.5 refrigeration piping and heat transfer components, ASME B31.8 gas transmission and distribution piping systems, ASME B31.9 building services piping, ASME B31.11 slurry transportation piping systems withdrawn, superseded by B31.4, ASME B31.12 hydrogen piping and pipelines, ASTM American Society for Testing and Materials, ASTM AT 152 standard specification for welded and seamless steel pipe piles, API American Petroleum Institute, API 5L Petroleum and Natural Gas Industries steel pipe for pipeline transportation systems, CWB Canadian Welding Bureau, EN 13480 European Metallic Industrial Piping Code, EN 13480-1 Metallic Industrial Piping Part 1, General, EN 13480-2 Metallic Industrial Piping Part 2, Materials, EN 13480-3 Metallic Industrial Piping Part 3, Design and Calculation, EN 13480-4 Metallic Industrial Piping Part 4, Fabrication and Installation, EN 13480-5 Metallic Industrial Piping Part 5, Inspection and Testing, EN 13480-6 Metallic Industrial Piping Part 6, Additional Requirements for Buried Piping, VDTR 13480-7 Metallic Industrial Piping Part 7, Guidance on the Use of Conformity Assessment Procedures, EN 13480-8 Metallic Industrial Piping Part 8, Additional Requirements for Aluminium and Aluminium Alloy Piping, EN 13941 District Heating Pipes, GOST RD, SNIP SB Russian Piping Codes, RD 10-249 Power Piping, GOST 32388 Process Piping, HTP Piping, SNIP 2.5, 6-85 and SB 36.13330, 2012 Gas and Oil Transmission Piping Systems, GOST are 55,990-2014 and SB 284.1 million, 325,800, 2016 Field Pipelines, SB 33.13 330 2012 Steel Pipelines, GOST are 55,596-2013 District Heating Networks, EN 1993-4-3 Eurocode 3 Design of Steel Structures Part 4-3 Pipelines, AWS American Welding Society, All American Water Works Association, MSS Manufacturers Standardization Society, ANSI American National Standards Institute, NFPA National Fire Protection Association, EJMA Expansion Joint Manufacturers Association, Intro to Pipe Stress https://web archive org/web/20trillion 161,8,161,619/http/okrejebelos com/metal expansion joints in